just discussing about the moving coordinate. Okay, and rather I can say that system of non-inertial frame. So a moving coordinate that can be considered as a non-inertial frame. Now from the first law of Newton's first law, that gives me some concept about the reference frame. And this reference frame is nothing but this orthogonal axis that are situated at a distant star. Okay, and these are considered to be a fixed one. Now, say for example, an event is happening at this point, which represents a point with respect to this reference frame. And now, the same event, someone, if he is observing with respect to another reference frame, but this reference frame is fixed at some distance star, but this reference frame is moving with uniform velocity. Say for example, the velocity is u. Okay. So, if anyone see both from both this coordinate system on this event looks like same, because the form of Newton's first law and the form of Newton's second law that are not changed if the system which is moving with uniform velocity, that does not produce any acceleration in the system. So the coordinate does not move in itself with some acceleration. So in that particular coordinate system, if you choose one is stationary and other is moving with uniform velocity, nothing, the form of Newton's law remains the same. So uniform motion with respect to a stationary coordinate system is not different from that of stationary coordinate. So even in this uniformly moving system remains same as we can see from this fixed coordinate system, right? So the application of Newtonian mechanics on a body that requires a reference frame, and the reference frame may be inertial and non-inertial, when the state of the body can be predicted with respect to a stationary coordinate system, right? So this reference frame, this is fixed reference frame, and that reference frame is situated on a fixed object. And if this stationary, this reference frame is moving, from which I am going to observe this particular phenomenon, that particular coordinate may be moving with uniform velocity or might have some acceleration. So if that particular coordinate system has some acceleration, we can consider this coordinate system as non-inertial one, and if this coordinate system moving with uniform velocity, then this coordinate system is inertial velocity, and Newton's law doesn't have any kind of problematic in that particular case. Now, this is why what happens when someone who is sitting on a particular train, if the train is moving with uniform velocity, the observer who is sitting inside the train does not feel any kind of effect until and unless he just peer outside. And when you peer outside, you can see that something is moving in reverse direction with the same uniform velocity. Okay, so if there is no indefinable force that are produced in this particular order system, which is moving with uniform velocity, but there exists some force. Say for example, this train is moving with some non-uniform velocity, which is a function of t. So some kind of acceleration is produced inside the train, and that particular acceleration basically generates some kind of fictitious forces, and that fictitious forces can be felt by the observer who is sitting inside the train. Not only the particular system moving in a straight line, but when this train is bent, what happens? There will be some centrifugal force. So this centrifugal force basically produce some kind of non-inertial acceleration, which are called simple force. Now, if someone is sitting inside the bus and the bus is moving, what happens? When the bus stops, bus is moving with uniform velocity, but when the bus stops, the person feels a jerk, and that particular time he feels some simple force, the presence of some simple force. Now, what happens when the coordinate system have a relative translational motion with respect to r? Okay, so first I have to consider a coordinate system in translational motion. So translational motion of a coordinate system, right? So we are choosing a coordinate system which is whose origin is O prime, coordinate system 1, and this coordinate system is designated by x prime, y prime, z prime, and this coordinate system is basically fixed. Now choose second coordinate system, that is coordinate system number 2, which have origin O, and that particular coordinate system have x, y, z, and this particular coordinate system are fixed with certain body. So this is fixed frame, this is body frame or the moving frame, because the particular body is moving with respect to one another. So I have to consider this coordinate system, and I am going to draw this two coordinate system here. So how these two coordinate system are situated? So let us consider that this is basically a prime coordinate system. This is z prime, this is x prime, this is y prime, and this is basically body frame. This is x, this is y, this is z. So this is O and this is O prime. Now, for a particular point which is chosen here, from this O prime coordinate system, the vector, the position vector is basically r prime. And from this point, this is r. And obviously, these two origins, they are separated by a vector capital R. Now, from this whole geometry, this frame is moving and this frame is fixed. So this is fixed, this is moving, right? So what happens? I can write that r prime, this vector, is basically r plus small r. Okay. Now, if you differentiate, this is assume that this equation is 1. Now, if you differentiate this equation with respect to t, you will get that r prime dot equal to r dot plus r dot. And if you differentiate with respect to t, not t prime, just t. And this r prime dot, this is basically dr prime by dt. This is basically dr by dt, that is dot, and this is basically dr by dt. Okay. So this is the first derivative of this equation with respect to t. Now take second derivative with respect to t. And what you will get? You will get that r prime double dot, this equal to capital R double dot plus r double dot. So this is equation number 3. So this is equation number 2. This is equation number 3. So what you will get, that the acceleration from this fixed coordinate system is equal to the particular acceleration of the object with respect to this reference frame plus the relative velocity between these two reference frames. So the relative acceleration of between two reference frames is r double dot, and this is r. Okay. Now consider Newton's law. Newton's second law. And this tells about the force is basically mass into acceleration, right? And in this particular case, if you multiply in equation number 3 in both sides by small m, which is the mass of a particular object situated at this point. So assume that at this point there is m masses object which is moving with respect to that particular coordinate system. So I can write that m r dot prime double dot equal to m r double dot plus m r double dot. Right? So this is the force which I see from this particular fixed point, and this force is basically equal to force with respect to r plus force from this system. So what you will see here, this Fr is the exact force which is felt by a body when it is moving in this moving coordinate system, with respect to this moving coordinate system. So Fr is basically Fr prime minus Fr. Right? So this is called the effective force. And this Fr, this particular force that arises due to relative motion of one coordinate with respect to the fixed coordinate system. Right? Now, if we can say that the situation is like that, that r dot equal to constant. R dot equal to constant means this frame is moving with respect to this fixed frame uniformly. So this frame has a uniform velocity with respect to this fixed frame. As r dot is constant, so r double dot in this case 0. So if r in this particular case 0, if r dot equal to constant. So if r dot equal to constant, I am writing this in a clear board. So what you will get? You will get that if r is basically if r prime minus a. So if r dot equal to constant, then if r will be 0. Okay. Now this if r will be 0, then if r equal to f r. So we will get this relation where this r dot equal to constant or uniform. Now what is r dot? R dot is basically dr by dt. That is the velocity of this unprimed frame with respect to prime frame. Right? So as this is f r equal to 0, I can say that Newton's law, second law, remain invariant. And at the same time, I can say no pseudo force is present in this case. Okay, so there will be no pseudo force in this particular system. So the system or the reference frame is called inertial reference frame in this case. Now if r dot is not constant, what happens? Then if r, this is not equal to null vector, and if r is not equal to null vector, then effective, this equal to f r, that is the particular force on the body which is measured from this unprimed reference frame, minus f r. Right? This is pseudo force. Okay, so this is the particular whole picture of a particular system that is moving with a constant acceleration. Okay. Now come to the part of a system which is basically have rotating, or the rotating coordinate system. So in this rotating coordinate system, first let us consider that unprimed coordinate system, that is O x y z, is rotating with angular velocity omega about some instantaneous axis passing through origin, right? So this unprimed coordinate system O, that is basically rotating coordinate system, and this rotating coordinate system is moving with just angular velocity omega with respect to some instantaneous axis. So this is the first proposition. Now there is another system. There is another system represented by O prime, x prime, y prime, z prime, and this coordinate system is fixed in space. So this prime coordinate system that is fixed in space, and this unprimed coordinate system that is basically situated with respect to in the origin, and that is rotated with respect to omega with some instantaneous axis. Okay, so for that particular system, for prime and unprimed system, if you move that prime system to the unprimed system and march their origin at the same point, so you are moving this prime system in space and in such a way that their origin are lying at the same point. So what you see here, let us consider this is a coordinate system which is basically prime coordinate system. So this is x prime, this is y prime, this is z prime, and this prime coordinate system is fixed. With respect to this coordinate system, the unprimed coordinate system is moving. So this is z, this is y, this is x. So this is rotating, this is rotating, this is rotating, and this is fixed. This is fixed, so this is fixed, right? So this x prime, y prime, z prime are fixed. With respect to that, x, y, z are moving, and this is some original origin. And you can choose the unit vector or the basis vector in this. This is a prime, this is j, not prime, this is a, this is j, and in rotating coordinate system this is I. In prime coordinate system this is j prime, this is a prime, and this is I prime, right? So now if you choose this thing in this way, you can write any vector in terms of either this ijk or ijk prime. So choose position of a particular point. So this is the position vector. So this position vector R, this can be written as I prime x prime j prime y prime plus k prime z prime, right? And the same thing, the same vector. So let us consider this is basically R vector. Okay. Now this same vector can be written with respect to this unprimed vector, so unprimed unit vector. So this will be I cap x plus j cap y plus k cap z. So both vectors are same, right? And the transformation equation from prime to unprime, this transformation is given by x prime equal to r dot I prime, y prime equal to r dot j prime, and z prime equal to r dot k prime. Okay, so this is the transformation from one to another. So what happens if you transform this equation? What you will get from this equation? This is I cap x plus j cap y plus k cap z dot I prime cap. So this will be x I dot I prime plus y j prime j dot. So this is not j, right? This is j dot I prime plus z k dot I prime, right? So now, if both the system are same, you can write I prime equal to 1 and j prime I prime equal to 0. So nothing will happen. But in this particular case, j prime I is not equal to 1 because this angle is not bilateral. Okay? Similarly, the same thing happens for k prime. Okay? So you get some definite transformation relation from the prime coordinate system to the unprimed coordinate system, right? Okay. Now, for if you consider any particular vector which is a function of time, then that particular vector v can be represented as any vector which is a function of t. This vector can be represented as I cap vx plus j cap vy plus k cap vz, where this vx, vy, vz are the three components of this particular vector vt. And the same vector in prime coordinate system, this will be I prime vx prime plus j prime vy prime plus k prime vz prime. Okay. Now, if you differentiate this term, this v, with respect to t in this prime reference frame, what you will get? Okay, you are going to differentiate this equation in prime reference frame. So what you will get? dv dy dt. This will be d by dt of I prime vx prime j prime vy prime k prime vz prime, right? So now if this I just transform the equation in from prime to unprimed system. That is, prime system here is moving and unprimed system is not moving. If if you choose this concept, then this prime unit vector, they are moving with respect to unprime coordinate system. And in this particular case, I can write I prime un Vx dot plus J prime Vy dot plus K prime Vz dot plus Vx prime di prime by dt plus Vy prime dj prime by dt plus Vz prime dk prime by dt. Now, this Vx, Vy, Vz, if this is these are not basically as this is a stationary coordinate system, so this term will be 0. What you will see as I integrate this term in fixed coordinate system. So this I, j prime, k prime are fixed. So as they are fixed, what you will get, this term will be equal to 0, and this will be I z Vx prime plus j cap Vy prime plus k cap Vz prime. Okay, now the same vector, for this same vector, I am going to differentiate this same vector with respect to in the moving coordinate system. So moving coordinate system is, this is the moving coordinate system. So this is moving, this is fixed. So what we will get? We will get that dvt by dt. This will be I Vx dot plus j Vy dot plus k prime Vz dot plus Vx di cap by dt plus Vy dj cap by dt plus Vz dk cap by dt. So you will get this transformation equation when you are moving from a prime coordinate system to the unprime coordinate system, right? So here you will you can see that the first term, what you will get in this equation, the first term is basically I cap Vx dot j cap Vy dot plus k cap Vz dot. This term basically represent the velocity of this particular vector if I choose the frame as inertial. So if you choose this frame, this unprime frame as fixed one, so this will definitely give me the velocity of any v vector. Now this particular three term, they appear due to the rotation of the axis. Okay, this three term. Now, as you see here, as this three term arises, now how could you encounter this three term? So let us consider the concept of rotating frame, and what you will get. Assume that this is the axis of rotation. So this represents omega vector if any particular thing is rotating with respect to in this circumference. Now, as this is origin, so any particular vector, let us choose this vector is r, and this vector makes an angle theta with respect to that particular fixed axis. Now, this radius vector that is moving at an angle d omega, and this vector have length or value r plus dr, right? So this is r vector, this is r plus dr. So if you draw this vector, represent obviously dr, right? So as that particular vector is dr, so what will be the value of dr? So this particular length, this length is basically r sine theta, and this is theta. And if the radius is r sine theta, so dr, if this angle is very small, d omega is small, then I can consider this arc with that must be equal to this length. So dr in that case will be radius times d omega. So r sine theta into d omega. Right? So if you differentiate this dr with respect to t, what you will get? R sine theta d omega by dt. Now what d omega by dt means? This d omega by dt is nothing but rate of change of this angle, that is rate of change of this axis or rate of change of this angle with respect to time. So this is equivalent to omega. So I can write dr by dt in terms of magnitude, that is omega cross r. Okay. From this particular point of view, I can write that this is equal to omega cross r. So as this is omega cross r, so as this is omega cross r, what about the previous relation? The previous relations in this particular case becomes for di by dt, I can write this as omega cross I, right? dg by dt, I can write this omega cross g, and dk by dt, I can write this omega cross t. Okay. So this vector dv by dt in fixed reference frame, this will be equal to dv by dt in rotating reference frame. As you see here, v vector is basically vx I cap plus vy j cap plus vz k cap. So dv by dt, this is basically vx dot I cap plus vy dot j cap plus vz dot k. So this is basically dv by dt. Same thing in rotating frame. Okay, so this is equal to dv by dt at rotating frame plus omega cross vx I cap plus omega cross vy j cap plus omega cross vz k. Okay, so this is basically dv by dt at rotating reference frame plus omega cross v. Okay. So now I can apply this formula for any vector. V is any arbitrary vector. Okay, so I can apply this particular formula in case of any arbitrary vector where, so there exists an operator relation. What is that operator relation? This is the operator relation. This is fixed equal to d by dt at rotating plus omega cos. Okay, so this is the operator relation between prime and unprime frames. Right? So this is the operator relation between prime and unprime frame. This is fixed and rotating frame. Okay. Now what you will see here, so if you differentiate twice, so from first differentiation with respect to t, we will get dv by dt at fixed equal to dv by dt at rotation plus omega cos phi. Now, second derivative with respect to t, what we will get, that is d square v by dt square with fixed, that is basically d by dt at fixed. So this is operator into dv by dt, this is vector plus omega cos v. Now this fixed operator can be replaced by this rotating operator. So this will be d by dt rotator plus omega cos, this is operator, times dv by dt plus omega cos. Now you have to break everything, all the. So this d by dt of fixed frame, this will be replaced by d by dt plus omega cross of rotating frame times dv by dt plus omega cos v, as v is the general vector. Now if you expand this whole term, this will gives me dv by dt square plus omega cross dv by dt plus d by dt of omega cross v plus omega cross v. Okay. Now if you differentiate this term, what you will get from this particular term? So this will be d omega by dt cross v plus omega cross dv by dt. If you expand this term, differentiate, you will get this two terms. Now this particular term is same as this term. Okay. One is arises from this and another remains in this equation. So what we will get? So d square v by dt square in rotating frame plus 2 omega plus dv by dt, that's also in rotating frame, plus d omega by dt cross v plus omega cross v. Okay, now if you assume that this particular system is moving rotating with constant velocity, then omega equal to constant. So as omega equal to constant, you can write this d omega by dt is equal to now written. So this dv by dt square in fixed frame, that can be represented as d square v by dt square in rotating frame plus 2 omega cross dv by dt plus omega cross v. Okay. Now, if v is any position vector, if this v is any position vector R. Okay, so if v is any position vector R, then of course what we will get, this d square R by dt square at fixed reference frame, this will be equal to d square R by dt square in rotating reference frame plus 2 omega cross dr by dt in rotating frame plus omega cross R. So you are choosing two frame, one is rotating with another. So this is prime, this is unprime frame, y, z, x, this is x prime, y prime, z prime, and you are choosing a particular vector R in this point, which is a position vector. Now, this fixed and the rotating frame are related by these two equations. So left hand side is basically acceleration in fixed reference frame, and this is acceleration in body frame. Okay, now this unprimed system is attached with that body, particular body. So the force felt by this body is particularly this times m. So if you multiply in both sides with m, what you will get? You will get this term. So this is basically the force in prime frame. This will be force in unprime frame plus 2 in omega cross dr by dt plus m omega cross r. Okay, so this F is the actual force felt by that body, as this is unprime frame, this is body frame. So this actual force, so F is equal to F prime minus 2 m omega cross dr by dt minus m omega cross r. So there are practically two fictitious force. One is this, the other is this. Okay, and ultimately this gives me F effective. Okay. So now we were choosing a system in this particular case. case. So how the system you are going to choose? You are choosing two coordinate system. One is just fixed here at some distant star. This is z prime, this is y prime, this is x prime, and some coordinate system is situated at here, but this coordinate system is prime coordinate system. So this is z prime, this is y prime, this is x prime, and this particular point is position vector r. Okay, now what we will get? This is r prime, this vector is r. Okay, now if there is no relative motion between two frame, only this frame is rotating with respect to any fixed axis through this point. Okay, what you will feel, what you will get from this, or from the concept of Coriolis force, this square r prime by dt square. This is fixed equal to this square r by dt square at fixed plus this square r by dt square at rotator plus 2 omega cross d r by dt plus omega cross r. So you will get all this stuff. So in operator form, I can write Rf double dot equal to Rf double dot, capital R double dot, plus R double dot plus 2 omega cross R plus omega cross omega cross R. Okay. And I said earlier that omega is constant. So omega dot r equal to 0. So this r prime f and capital R f, they are basically acceleration relative to fixed axis. So this is acceleration relative to fixed axis. This r f, this is linear acceleration of this unprimed frame with respect to this prime frame. So this will be unprimed frame. So acceleration of this unprimed frame with respect to this prime frame. Linear acceleration. This r basically acceleration in unprimed frame. Okay, and this r dot basically the actual acceleration of this body with respect to this frame. Now, this 2 omega r, this is called Coriolis acceleration. This particular term arises for the rotating system. Okay, so this is called Coriolis force, and if there is no rotation, there is no acceleration of the particular system, then there will be no Coriolis force. And omega cross r, this is basically centripetal acceleration. So this last two term, basically arises in rotating frame, and this Coriolis force, this is a particular interest because this is one kind of pseudo force. Many natural phenomena like the wind or the displacement of some particular object in the northern hemisphere at its east side, that is due to this Coriolis force. I will discuss the whole thing in some later class. So up to this,